Hello everybody and welcome to Exam School. Today we are going to be tackling all of the questions that you asked on the previous show regarding physical science, and I'm sure that you guys are all tuning in, and we are going to try and answer as many as possible because John is actually with us in studio right now. Hi John.
Hi Pumi, how you doing?
I'm good, thanks. How are you?
Excellent. Now guys, I know that some of you might just be tuning in and you might have been expecting grade 11 accounting. Unfortunately, we can't bring that to you today. We're bringing it to you next Wednesday at 6 o'clock. So please tune in for that, check the schedule, and we've had to make that little adjustment. But today, because the grade 12s are writing physical science, paper 1, that hard physics subject, we're going to answer some of their questions. We ran out a little bit of time in the last show. So
Yeah.
for me, I'm really excited because I've been sitting on Facebook for the last hour and a half and checking all the questions, and there's some really great interaction. Now, what I've noticed is that there are mind setters, that are answering other people's questions. And that's a great way of learning as well. So carry on asking those questions. Unfortunately, I won't be able to take any more questions. You see, I've got them up here on the board. I've taken them and I've put down people's names, taken them directly from Facebook, pulled them into the show, and we're going to discuss them and hopefully just add a little bit more to those questions so we can deal with the concepts. But if you want to add something and comment to Pumi, then please do that. Post on the page as well, and she'll pick it up and have a conversation, and let's see if we can sort out these key areas. Okay, Pumi, you ready?
Absolutely, I am ready. But before we can get to that, John, I know we're all excited and we really want to get on with the learning. But I need to quickly remind you about this K53 hashtag Be a Bright Spark competition that we are running. It is closing next week, Friday, on the 15th of November. So all what you have to do in order for you to win the Chevy Spark L is all what you have to do is, one, buy the SafeWays K53 application from your Samsung Galaxy app or the Google Play Store. Or if you like, you guys, you can always buy this book from any retail store and keep your receipt as a proof of a purchase. And then straight after that, at number 2, all what you have to do is just to like us right there on our Facebook page. It is facebook.com/learnextra and facebook.com/SafeWaysK53. Make sure that...
Can I just interrupt you?
Oh, yeah?
On the Facebook page, guys, there's a tab that says win a car. You need to go in there and fill in your details. So please don't just like the page. That would be great. We'd love you to like the page, but you need to enter the competition. So don't just like the page and think that you've entered the competition. You need to go onto the tab that says win. It's the second tab right at the top. Press that, enter your details.
Absolutely. Thank you so much, John. Like the page, fill in your details, and from there on, share it with your friends because that will automatically earn you an extra entry. Without any further ado, guys, please, let's just get straight to the questions.
Thanks so much, Pumi. Now, if you've got other questions, we've broken them down into different sections. I'm going to start dealing with vertical projectile motion. So, Pumi, if you're watching the page and you're watching all the inboxes, if there's anything about vertical projectile motion, free fall, anything like that, graphs of motion, equations of motion, let me know.
Great
and
stuff.
we'll try and help it. But just watch for a little bit and then see if you understand. So Bongi had the first question, and she was right out the starting blocks. She says, when it comes to the graphs of motion, okay, let's just get the pen up. So the vertical projectile motion, I never know which one to draw. Do I distinguish between them all? Please help. So that was what Bongi had to say. And we had a follow-up question, which was from Silunudu, okay, Mangaliso. And he says, or she says, I'm not sure, vertical velocity versus time graph by a bouncing ball. And then Tracy also wants to know what is free fall. So we're going to try and answer those questions about vertical projectile motion. So first of all, what do you think vertical projectile motion is? You should know at this stage that the important thing when we're dealing with vertical projectile motion, it's all about taking an object and pushing it up, throwing it up, or taking an object and dropping it down. And the critical thing here is that the acceleration due to gravity is going to be 9,8 meters per second downwards. Okay, so before I carry on to say anything else, the most important thing, if you're going to do a vertical projectile motion, whether it's a multiple choice question or whether it's a long question, you need to decide which is your positive and which is your negative direction. And I know this is something that lots of learners battle with. Once you've decided, you must keep that sign constant for the whole question. So if I decide up is positive, that means down is negative, then I must keep it for the whole question. Now, how do you decide? Let me give you some advice. What I say to learners is if the ball is being thrown up, then there's two motions usually, because it's up and then it falls down and it carries on down. Then I'm going to make up positive and down is negative. That would be easy. The only time that I allow learners to make down positive is if there's only one motion. So if a ball drops and hits the ground and doesn't stop moving, then that's fine. Then make down positive. But if it's a bouncing ball, then I still like to have down as negative and up as positive. It just makes sense to me. Okay, so let's just make sure that you've got the key point of direction. So now when we come to graphs, if we've decided the direction, you've defined your direction, then you don't have a problem with deciding where you're going to start. So let's just go to the three different types of graphs that you're going to go, and we're answering Bongi's question. So Bongi, the three graphs that you can get asked, or you can be given, or you can be asked about, you could be asked a change in position versus time graph, you can be asked a velocity time graph, and you can be asked an acceleration time graph. So let's take a scenario of a ball being thrown up. Now, I need you to understand something very important as far as vertical projectile motion is concerned. The graph starts the second, the instant, the nanosecond that the object leaves your hand. After the object has left your hand, there is no force from the hand exerted on the object, or the rocket, or whatever it is, the catapult, the elastic band. Once it's left that position, there's nothing that's going to be pushing it up. So when an object travels upwards, the only force that is acting on it in the absence of air friction, and we'll deal with air friction in a minute, is the force downwards due to gravitation. The Earth's gravitational field attracts anything that has mass. So let's make sure that we understand that there's a downward force because an object is traveling upwards. It doesn't mean that the force has to be upwards. The force is actually downwards. Now, if we had to include frictional force, air resistance, we recognize that air resistance opposes all motion. So if we have an upward force, an object falling upwards, being thrown upwards, not falling upwards, being thrown upwards, then the air resistance, frictional force, will be downwards, as well as the force due to gravity would be downwards. So the net force would be downwards. We don't find that when we throw something up, it suddenly carries on going. No, it gets to a maximum height, and then it falls back to Earth. Now, let's be very clear about it. So if we're starting from the position of the ground, and we're saying that's my position, and we're going to say, what happens to this object? Well, I'm throwing it up. As the minute it leaves my hand, it's going at its maximum velocity. So it has maximum speed and it starts to slow down. So the graph is going to look something like this. Let me explain what's happened in that graph. It started moving upwards. It reached a maximum, which is about, in this case, about there at that time. And then it changed direction. It moved a certain height and it started coming back down to the Earth. So after these number of seconds, however many that is, could be 1 second, 2 seconds, 5 seconds, depends on how high it's gone, depends on what velocity it left the hand with, the object will travel in that way. What do we know, guys, when we look at this graph? We know that there is a change in the speed or the velocity. How do we know that? And I want you to look carefully at the graph now. I'm going to use my pen and hold it next to the graph, because this is a curve, but I hope you can see that holding it there next to the curve, and maybe even if I draw a straight line, let me try and do that. Over here, I'm drawing a straight line at that point, and a straight line at that point, and a straight line. What do you notice about the gradient of those straight lines? Did you notice at the beginning it was very steep, and then it fell over a little bit, and then it fell over again? Now, in fact, what it was doing was that, and then that. Look at my arm. Straight up, then that way. So the gradient going from this side to that side in that direction is a positive gradient, and it's getting less. It's going to, when it's horizontal, to 0. So what we recognize is the gradient of this graph, and let's just pick up the pen. The gradient of this graph, the change in x over the change in the change in t, is going to give me the velocity. So the gradient of that graph, even though it's a curve, we know from calculus as well, it's the derivative of that, that is going to be the velocity. So the displacement gives us, the derivative of displacement gives us velocity. And what I'm trying to show you here by looking at the gradients is to say, hold on guys, we're going to start with a positive velocity. Over here, it's going to be positive. Because remember we said up is positive. So here, this object starts with a positive velocity. It's moving upwards. Then what did we notice? It gets less, it gets smaller. The gradient has decreased until it gets to 0. Now, what do you notice is happening when we get on the other side of the 0 mark? Look here, what's happening to the gradient? Can you see that the gradient is now lying this way? It's lying in a negative direction, and it's getting bigger. So on my graph of velocity versus time, my velocity will become negative, and it will get increasingly bigger. So in fact, what I've got is a straight line that passes through a point. Now, my straight line wasn't drawn very well, so let me just draw those points again and just make sure that you've got that very clear. So let's get the white pen out and redraw that. I've plotted the points, and I'm saying my line is a straight line that has a negative gradient. Hope you can see that the whole line now, the velocity time graph, has a negative gradient. And what do you know about the change in velocity over change in time? Well, the change in velocity over change in time is the acceleration. So the acceleration graph over here, well, let me not use that one. I wanted to use that one. The acceleration graph is a constant acceleration. Does that surprise us? No, it shouldn't, because the acceleration we know is constant. We've mentioned it back over here. It is negative, or 9,8 meters per second downwards. And we've said down is negative. So that's why this is negative 9,8 meters per second. Now, there's two last little things that I want to mention about graphs of motion. Please, if they give you a graph and they ask you to calculate the gradient, don't think you've got to use this value. You use the value from the graph. And in previous exam papers, it's come out to be 10. So don't be surprised if it's 10. Even if it's 10,1 or if it's 9,7. That could just be because of the way they've plotted the graph. Use the information that's been given. It will be around about this value of 9,8. If you're doing any calculations, though, that are not related to the graph, then you must use 9,8. Do not ever use 10 in a calculation. Okay? Only if it says from the graph calculate. But if it's not giving you the graph and you're asked to substitute, you must calculate using 9,8 downwards. And then the last thing that I just wanted to mention was the bouncing ball, very quickly. Bouncing ball looks like this. Let's just draw the graph, and this time it's the displacement time graph. We're going to say we start from a positive height, it bounces down to a 0 position. Now it's going to have a moment of contact with the floor, and then it's going to go up, and it's going to come down again. That's your change in position or displacement, change in x over t. Your velocity time graph for that would look something like this. Let's plot it out. You'll see that it starts with a negative gradient, and the negative gets bigger. So what we notice here, the negative is getting, over there it's 0, and there it's getting, and so it starts from here, it's getting more negative. What happens over here? Well, it jumps to being a positive. So we get this sort of arrangement with a velocity time graph with a bouncing ball. Now, I'm out of time in terms of this particular question, but I hope that's been useful for you. Please remember one last thing, that when a ball gets to its maximum height, its velocity might be 0, but the acceleration throughout the whole period, whether it's a bouncing ball or not, while it's in the air, its acceleration is always 9.8 meters per second downwards. If we had to draw the acceleration graph, we would see that the majority of this time is going to be negative 9.8 meters per second. The trick is what's happening on the floor. Sometimes they make a funny thing about that. That could be a very big positive value because the floor is pushing on the ball, and so you could get little dots right up at the top. Okay, Pumi, we've tried to summarize that as much as we can.
Awesome stuff, John. Thank you so much. All right then, guys, we'll see you shortly after this break. Welcome back, Mindsetters, from that very short ad break. Right now, we are still doing physical science and we're answering all of the questions, or rather, we are trying to answer as many as possible of the questions that you asked earlier on the show. John, I want to ask something. How important it is to try and draft make the figures of what's written, of what is asked in a question? Like if they asked you about a ball and a building, do I really have to illustrate all of that? Will I get enough time?
Let me be very clear. I believe it's really important to do a rough sketch with every physics problem. But your artwork isn't the important thing. What is important is that you put in all the information. Now, if it helps you and you are a slow worker and you know that you're going to run out of time, then use the diagram of the question sheet, because the markers are not going to mark you for your drawing. So you can use the diagram on the question sheet and fill in everything on there. That might save you some time. But please work with the diagram. It is so much easier to think of your thinking through when having worked on the diagram. Okay?
Awesome stuff.
Okay, cool. Now, the next section. Guys, we have done a little bit on vertical projectile motion, graphs of motion. Remember some of this? The equations of motion comes from earlier work in your grade 10 and 11, but the vertical projectile motion comes from the beginning of the year. So if you're needing more help, post some questions on the page. We'll try and get to them, but I'd really hope that we've finished with this topic. There are lots of resources on the Mindset website. If you're still struggling, we'll try and help you as much as you can. Go and look for those resources, look for those extra lessons, and even ask some help from other Mindsetters. But for the moment, let's move on to our next topic. And the topic that comes up next, Florence and Neo, they both asked about electrodynamics. So the one is asking about, please explain Fleming's rules and how to apply it, and the other says explain electrodynamics, and those two mean the same thing, the basic motor and the generator. Guys, to a certain extent, this is bookwork. This is something that you've got to have a picture in your head, but I'm going to go through it very quickly. There are different ways that people remember, and there are different rules that people remember. If what I'm going to tell you now is something that you're not familiar with, then ignore it. Switch off and remember the thing that you've been taught. If you haven't been taught it, then listen carefully to what I'm going to say to you. Now, with electrodynamics, we've got to start at a particular point. And the particular point is we've first of all got to recognize that when there's a current, around a current, there is a magnetic field. Okay? And what I need you to understand is that we sometimes have symbols for current and magnetic field. This is grade 11 work, and we're just going to revise it very quickly. We're going to say if that's a conductor, and let's make another conductor over there, then if the current is going into the board, then we say it's going in. It's like looking at the back of a dart. And if you've ever played darts on a dartboard, if you look at the back of a dart, like I'm throwing towards there, I will see the feathers of the dart. So that's why we see the cross over there. If I'm throwing the dart towards you, you'll see the point of the pen coming towards you. Okay? And so if you see a dot like that, this means in to, this means out of. Okay. Now, if the conductor is a straight conductor, then what we recognize as around the conductor, there's an electric field. And we draw the electric field as a region of concentric circles. And they're close together to start with, and they spread out further as we get further away from them. So you will remember seeing diagrams like this. And we've got to show the direction of the magnetic field. The direction of the magnetic field is determined by a compass needle. So if we put a compass needle here, which direction will it point to show us the North Pole? And the way that we do it is we use the right-hand rule. Always the right-hand rule. I find it really easy with this section to have one rule. And the one rule is the right-hand rule. I know that there are textbooks that say you can use the left-hand rule, but that can be confusing. I will try and distinguish between those a little later. So right-hand rule, we say, look guys, we've got one current. So the thumb is one current. It's measuring, which way is it going? It's going into the board. So the direction of the magnetic field is in the curl of the fingers. So in this case, it is a clockwise direction. So the magnetic field is in that direction down that way. Okay? All the way around. Taking it this way, magnetic field coming out of the board, it's going round that way, it's anti-clockwise. You need to practice that and recognize what's happening there. Okay, so very important to recognize the relationship between current and magnetic field. We did this in grade 11. Now, what you've got to recognize is that in grade 12 we've taken a little step further. This still applies. This absolutely applies. But instead of just having two parallel conductors, or two separate conductors, we say, let's join them. And the picture, now you'll see that my artwork isn't very good. The picture is of a turn or a coil. It's sometimes called, I can't even remember the name of it, but it's a ring, okay, that we're saying. And this picture up at the top is like a cross-section through those two. It's a cross-section, it's cut through, and we're looking end-on at it. Okay? Hope you've got that. Now, guys, if we connect this cross-section to a battery, this thing, and we allow it to spin and we allow it to move, then what we'll say is let's make this the positive end, because that will take the current in. Remember, conventional current means that it goes from the positive terminal to the negative terminal. So if it's going from positive, it will go all the way around there. It will be coming out on that side, and those two diagrams match up. For me, is that making sense?
Yep, it does.
Okay. So I hope you're following me now, because this is the extremely important thing. We've got a magnetic field associated with that. In grade 12, what we say is, guys, and this is something that Michael Faraday did. He said, well, we know that there's this magnetic field. What happens if we put a permanent magnetic field in the path of these conductors? If we have two magnetic fields, well, what happens when you have two magnetic fields? Two magnets, you're going to get attraction and repulsion. Okay? And that's exactly what happens to a certain extent over here. So in this grade 12 section on electric machines, electrodynamics, we say, guys, let's put a north pole over there and let's put a south pole over there. Permanent magnets, and we're putting the coil or the armature, sometimes called the armature, that coil thing, the word I couldn't remember just now, into this permanent magnetic field. What's going to happen? The explanation I'm going to give you now is called the motor effect. Because what happens is that because there's a permanent magnetic field and because there's a field associated with the current in the conductor, the two interact with each other, and there's a third thing that happens. You've got current, you've got field, and there's a force that is produced. So briefly, if I say to you, we know that the magnetic field lines in a permanent magnet run from north to south. Okay? We say they run from north to south, across that. So you can imagine across this diagram we've got field lines. Now you'll see that in some cases, at the bottom here, if I have, and I'm going to draw it in a different color, a straight line going through there, or perhaps green wasn't the best color to use. Let me just undo it and let's use blue. Okay? What do you notice? At the bottom of this diagram, this field is going that direction. Notice this one is going in the opposite direction. They're going to hit each other head on. And in a sense, they're going to cancel each other, or they're going to try and push past each other. And magnetic fields can't push past each other. They can't add together. They have to bend to get out of the way. In this case, what we find is that one's going this way, and this one's going that way. So they're strengthened. There's more magnetic field over here. And over here, this one's being pushed to get out of the way. So it kind of does a little bend, but nature doesn't like a bend. So if this thing can move, what happens where they collide like this head on? Then there's a force that causes them to get out of the way. And that force is going to push this side up. And because there's more on this side, I could have done another blue line on the top here. And you'll see if I do the blue line on the top here, you get a collision over there. You get the strengthening on that side. So what's going to happen? There's going to be a force downwards on this side. So force up on that side, force down on that side. Now, guys, you haven't got time in the exam to work all of that out. If it's on a spindle, a rotating disc, then what you're going to get is the armature moving up on the one and down on the other. But you, as I said, you can't just try and work that out by drawing pictures in the exam. So we need a summary. Now I'm going to show you the summary now. And again, we use the right hand. Notice I'm left-handed, so I put the pen in my writing hand and I lift the other hand. So I know that I've got the right. If you're right-handed, lift the hand with your pen, and then you know that you've got the right hand. Don't get the hands mixed up. So what are we going to do? We're going to use the right-hand motor rule here. Okay? And the way that we're going to do it is we're going to say to ourselves the following things. It works for motors and generators. The right hand you can use and not have to do anything else. Watch what I'm going to do. I'm going to say to myself, now the field is going to be, I'm wanting to find the direction of the path. So take a look at this. If I'm using the magnetic field, the permanent field, from north to south, I use my many fingers to show that. I'm then going to say to myself, in which direction, let's just be very clear here. So we do that in the direction of the current. We do that in the direction of the field. And then we're going to say the direction of the current is into the board. It's the flat. Actually, I've got this mixed up. I'm just wanting to make sure that I've got it right. So let me just follow this carefully. So if we're going up over here, then I'm really a little bit lost in terms of where I've made a mistake. No, it's fine. I'll sort it now. Let's just try one other way of doing it. If we take the first finger and we say first finger is the direction of the field. I just want to confirm it for myself. The first finger is the field. The second finger is the current. So this is the one that I point in, and the thumb points upwards. So if you can check it, and that's just what I've done because I got lost with the other one. I recognize the field is in that direction. The thrust for the thumb is up, and this finger, the second finger, is for the current. So remember, for the right hand motor rule, we are going to, sorry, I'm just thinking now that maybe I've made a mistake, but I don't think that. I think that's right. Please let's just leave that for a second. I will come back and just check it. I've got myself all tied up in a knot, and I don't want to confuse you any more than I have. Okay, so please remember, we're going to apply the right-hand rule. I will demonstrate it for you shortly. There was one last thing that I want to say about motors. And that is that how we get this thing moving, how we get it turning, it's a very important feature of motors that are DC motors, direct current motors. We call it a commutator. Please take note of this. A commutator is the device that we use to get the current in. We're only talking about direct current machines at this stage, direct current, and we're recognizing direct current goes through a commutator. In fact, a commutator is a little half turn that's got a gap in it. And the reason that we have the commutator is it allows the armature to spin freely. It allows the armature to spin freely through 360 degrees, so that it means that the current on this side, closest to the north, is always going to be in, and the current closest to the south is always going to be out. Hope you've got that, guys. So the distinguishing factor about a DC motor is that it will have a commutator, and please try and remember that we use the right-hand rule all the time. Okay, and I will explain that rule. I just need to check something to make sure I'm not getting it wrong. The next thing that I want you to say to you is that we can turn the motor around into a generator. Turn it, if we turn this construction, this motor, we will produce direct current. So DC motor, DC generator has the same construction, and in both cases we use the right-hand rule. Okay, Pumi, let's take a break, and I need to check my notes.
Okay, let's take a break, guys. I'll go and drink a glass of water while John is off to check his notes. We'll see you after the break. Welcome back from the break, Mindsetters. I'm ready. John is ready. I'm hoping that you are also ready to tackle the other part of the work right now. John?
Thank you so much, Pumi. Now, guys, I've had a think, scratched my head, tried to remember something. So let's go through this right-hand rule, because you can see there have been lots of things written in textbooks, and it really is a little confusing. I'm going to try and clarify that confusion now. So if you're going to use the right-hand rule for this motor, then it's a DC motor. Remember what you are given. You are given the direction of the current. So the thing that you're given is the direction of your fingers. Now look here. If you're given with the right hand, I'm pointing in. Then the magnetic field is the direction of the thumb, and the palm points to the unknown. So if the palm is up, try it on this side. You're given the current, it's coming out. The field isn't pointing in that direction, it's pointing in that direction. So which way is it going to move? It's going to move down. Okay, so bear that in mind. With a motor, you're given the current. You use the thing that you are given. Okay, now, the last thing that I was going to say to you is that's DC. What is the difference between DC and AC? AC means alternating current. And we haven't got time to do too much on AC, but just simply to say, alternating current means that the direction changes. The direction of the current changes. Direction changes, and direction of the current, I, changes. And it changes very quickly. It's 50 hertz, 50 times a second. That's what we get from Eskom. Now, with an AC motor or an AC generator, you don't have a commutator. You have something called a slip ring. Now, with this generator, you want to use the right-hand rule as well. Now, with a generator, you're not given the direction of the current. You are given the direction of motion. So if you were given a generator and you were asked to see what happens, the direction of the current with the right-hand rule, you would have the armature ends over there and there. And if you were told this thing is rotating downwards, that side is going upwards, what are you going to do with your right hand? You're going to say, I know the direction is down. I know the magnetic field is north to south. Okay? There's north to south. And I know that's the direction. So which way is my palm pointing? My palm always points to the unknown. The palm is pointing inwards. So that tells me that the current must go in on that side. And on this side, it's going up. So point upwards, field is that way. Which way is it coming? It's coming out on this side. I hope you can see there's that relationship using the right-hand rule. Now, there is another right-hand rule that I want you you might have seen in textbooks. And this right-hand rule looks like this. Right-hand rule like this is generally used for generators because most people are generally right-handed. So if you know this one, you can use that for the generator, and then you use the left hand for the motor. I don't like doing those two things because it really gets confusing about which one to use. But it might help you to remember generally right-handed generator gen. Okay, maybe that will help you. Okay. For those people that asked about electrodynamics, I hope we've clarified that. Let's quickly move on to one or two other little things that talks about cost of electricity. And there's even somebody here, Mwele Bandizi, has given us an example of a cost of electricity. Thank you so much for giving us this practical example. So now, guys, what you need to recognize with cost of electricity, you are told that units of electricity are sold in kilowatt hours. And that is a unit of energy. Okay? Because if you look at it, it's got a power unit times a time unit. But they're not standard SI units. Remember the standard for a SI unit for power is a watt. The standard for time is a second. So you're going to have to play with this because it's now in kilowatts, which is 1,000 watts, and hours, which is not just 60 seconds, but 60 times 60. 60 seconds to give us a minute times 60 to give us an hour. So you've got to do some conversions. So perhaps let's just quickly take a look at this tumble dryer question. We're told that it has a rating of 2,600 watts, and it runs for 3.5 hours. So the first thing I'm going to do is ask how much energy is being used. And I'm going to say work or energy produced is the power times the time. Please just, I've quickly substituted like that or changed the subject of the formula. If you're going to do it in the exam, please don't do that. Use the equation that is given on the data sheet, fill it in, substitute, and then multiply out. But I think this is just easier for our explanation. So we're going to say 2,600 times the time, and here the time was 3.5 hours. But guys, we can't just work in units. Here we've got to have 3.5 hours. So let's multiply by the 3.5 hours, 3,5, and we'll remember now that this will give us a value of watt hours. So let's multiply it out. Let me get the calculator. If it's still here, there we are, it is. And we're going to say 2,600 times 3.5, okay? That will give me that number of watt hours. I must divide by 1,000 to give me kilowatts. So if I divide by 1,000 and we push that, we'll see that it's 9,1 kilowatt hours, okay? Now we've got that unit. We say 9,5 9,1 kilowatt hours. What's the cost? Well, the cost is R1.04 per kilowatt hour. We establish the number of kilowatt hours, then we're going to find what the unit cost is, and it's a simple question of saying kilowatt hours multiplied by the cost, which was, what was it there? R1.04, and we get the final answer to be 9,464. We must round off to rands and cents, so it's 9,46, and that would be the answer to that. Hope that makes sense. Please remember that in this case, some of you may have been tempted to convert all the way back to seconds. You don't have to do that because we're dealing with kilowatt hours. If they gave it to you in minutes, then convert it to hours, multiply the power value by hours, and then just divide by 1,000 to get back to kilowatts. Okay. Last question on this page was, can you do an electricity problem involving ratios? It's a little difficult, but I will try and do one just to mention to you. It's not advisable to do it. If you know that this is a potential difference of 12 volts, okay, and you were told something like this is a 3 ohm resistor and this is a 9 ohm resistor, then you should know that the bigger resistor gets the bigger potential difference. The ratio of resistance is 1:3. So that means there are 4 parts. We have to divide the potential difference into 4 parts. And I'm sure you can see that you're going to need total of 4 parts. And we're going to need 1 out of 4 times 12 over there. And we're going to need 3 out of 4 times 12. And if we do that, this one comes to 9. So the potential difference across here, the potential difference, voltmeter reading, is going to be 9 volts. And obviously then the potential difference on this side is going to be 3 volts. Okay? So make sure that you've got that if you want to do with ratio. If you don't know about ratio, don't do anything new in the exam. Use the old way of doing it. Please do not do anything new. Okay, next one, forces. I don't know that we've got time to do all of them. There are lots of different types of forces. Some of them are contact and some of them are non-contact. And you should be able to identify them. The most common ones are going to be those things that a push or a pull. A magnetic or gravitational force. Those are the 2 examples that I want to give there. And you should really be able to, friction is another example of a force. So please be aware of these different types of forces. How do we calculate the net force? This is a very important question, so I want to take a little bit of time of it. If we've got a free body diagram, please, if you're asked to draw a free body diagram, which is possible, then you need to write down all the forces acting on an object, okay, and label them. So this one would be the normal force, this is the force due to gravity, this is the force of friction, and this is the applied force. Now, similarly to this question, there was one about do we always have to put things into components? Well, if I'm going to add all these together, if they're not at 90 degrees to each other, yes, I do need to put them into components. Remember that if you've been given a force like this, doesn't matter what it is, you can break it apart into its horizontal and vertical component. And the way that we do that is we complete the triangle and we say we want that angle there, and we can therefore say the vertical component of this force is going to be the force, if that's the force, force times sine of theta, and the horizontal component, this is F horizontal, is going to be F times the cosine of theta. You must be familiar with breaking things into components. When I look at components and I look at a free body diagram though, please never put the original force and its components onto the same free body diagram. We normally use components when something's on an inclined plane, and it makes it really easy to calculate. And I think that comes to one of these last questions here, where Sipiwe or TC says in question 1 in the previous show, Tracy did, can we use equations of motion? Now, if you go and look at that question 1, what you will see is that you are told that the object goes from a meter above the ground. We can't use the acceleration due to gravity, but we can use the component parallel to the surface, which means that we're going to break down the component of the vertical and say, what is the component that is parallel to the surface? So we complete the diagram. That one is perpendicular. This one is parallel. That's the angle theta, which happened to be 30 degrees. That was, you're going to use sine theta there because it's opposite. This was G parallel. And if you can say that this is G, the G parallel is going to be equal to G times sine theta. Okay? In that case, once you've got the component parallel, yes, you can use equations of motion, and an equation that would work would be final velocity equals the initial velocity squared plus 2a delta x. Okay. For those that you didn't get that didn't get the question from the previous show, then please download the notes. It's question number 1. This is an alternative way of doing it. The memos are on the notes as well. It will be repeated at 9 o'clock this evening, so please make sure you tune in for that. Okay, let's do one last thing. We've dealt with components. I hope that Lesedi, Mumu, I've dealt with that. How to calculate the net force. Okay, net force, last one. If we have different forces and they're all one after the other, net force just simply means, can I have one force that will replace them all? One ring to rule them all, okay? Now, we're not doing Lord of the Rings, but you get the idea. But now, if they're not collinear, or even if you've got one in that direction and another in that direction, what's the angle between them now? Well, let's first of all answer the question, what's the angle between these? The angle is 0. So if these were the forces acting together and we were doing work with them and they're in the same direction as the displacement, for the work energy theorem, we would use cosine and cosine theta. There the theta would be 0 because they're in the same direction. I'm just trying to answer somebody else's question. If they're in the opposite direction, then they're at 180 degrees. Then you're going to use opposite direction cos of 180 degrees if you're looking at the work done and it's in the opposite direction to the displacement. Okay, that was just an aside, and I hope that you've got that if you were looking for that, because I'm not going to get to that page. So what's the net force going to be here? Well, you're going to need to decide on direction. In this case, they were all in the positive direction, so it was easy. You're going to have to choose. Those two is positive and that one is negative. Add them up and you get F net. Now, that's all very well, but what happens if you've got forces that are not collinear? They're not in the same direction. So you've got a force in that direction and you've got a force in that direction. How are you going to add these forces together? Well, the easiest way to do it, and the way that you've probably been taught, is let's take this force and let's break it up into its components. So it will have a component in that direction and a component in that direction. We add these two forces together and we get a single force in that direction and the component in that direction. Now what do? Well, guys, we've got two things at 90 degrees. We're going to use Pythagoras. We say, Pythagoras, there's your triangle. You use Pythagoras and you use the tan of theta. And that's all the time we've got. Thank you so much for being with us. Pumi, over to you.
Thank you so much, John. I really had a great time in trying to understand physical science, and I'm hoping that you guys are going to do very well and make us proud tomorrow when you're writing your physical science paper. All right, then, guys, it's been an absolutely amazing show, and please remember to stay tuned into the next show that you're going to be having. We are going to be doing geography. Without any further ado, this is a show brought to us by MTN SA Foundation and also endorsed by the Department of Basic Education. It's been absolutely great to be with you guys. See you next time. Bye-bye.